Hi, this is Mr. King. I'm going to do a short tutorial on graphing sine and cosine using the GQA, the graphing quadrantal angles. Graphing transformed sine and cosine functions is straightforward if we focus on only graphing points at angles with well-known values. For the parent functions of sine and cosine, the period is 2 pi. Over this period, each function has 5 quadrantal angles: 0, pi over 2, pi, 3 pi over 2, and 2 pi. At these angles, the sine values are 0, 1, 0, -1, 0. And the cosine values are 1, 0, -1, 0, and 1. The angles are equally spaced, and the values are simple to retrieve from memory or from the trig or unit circle. To graph a sine or cosine function with transformations, one simply adjusts the 5 quadrantal angles to account for the new frequency, hence period, and any phase shift. The steps are listed below. So the classic sine or cosine function with transformations is represented here. In this sine function, we see that there is an amplitude A. Well, it could have a negative in front of it too. Remember, the amplitude is the absolute value of that number. And the B value is the frequency, the C value is the phase shift, the D value is the vertical shift. The same holds for the cosine function here. So here are the steps. Our first step with a transformed sine or cosine function is to rewrite the function so that we can see each transformation value. And that means we want to put those functions into the forms right here. Determine the period is the next step, and this is a pretty simple task. We divide the normal period of 2 pi by b, and so the period is 2 pi over b. The next step, divide the period by 4 to find the new quadrantal angles, the NQA. These angles account for the new length of the period. We're going to next adjust the NQAs, the normal quadrantal angles for the new period, by applying the phase shift, which is the C value. And that can move all of the quadrantal angles to the left or right, depending on if it's a shift left or right in this phase shift. Next step is to adjust the normal function values at each normal quadrantal angle, each NQA. Remember again, the normal quadrantal values for sine are right here, and for cosine they are right here. These values will need to be multiplied by the amplitude, and we'll have to also apply the vertical shift, which could be up or down. And so that means multiplying the normal values by the A value and then adding the D value. The next step is to get the grid ready for graphing, and for this we're going to custom label the graphing grid. These won't be normal graphing grids that you might be used to, because we're going to make them custom for the NQA angles. And I'm going to demonstrate all of this in just a moment. We'll then plot the 5 points that go with the 5 NQA, the 5 graphing values, and we'll duplicate that pattern once. That will give us 2 full periods for these graphs. And then we'll sketch in a nice smooth curve that looks like a sinusoid it looks like a wave. So let's take a look at an example now. So in this case, we have y equals f of x is 4 cosine of 3x minus pi over 4 minus 1. Now that may look daunting at first. If you haven't graphed many of these, it probably does. Well, first of all, let's go back and see what we're supposed to do. We want to put our function into this standard form where we can see all the transformations clearly. In this case, we can see that the frequency is 3 here, but the phase shift is not directly obvious unless we're used to working with fractions and distributing in our minds, in our heads. So what I like to do is this, and this is what I'd like to see you guys do, is rewrite this, factor the 3 off the x, and factor the 3 out of the pi over the 4. And when we do this, we get 4 cosine of 3 times x minus pi over 12 in parentheses minus 1. Now, if you're not sure if you did this right, you can always distribute the 3 back in to see if you get back to where you started. Well, 3 times x is 3x. That's easy to see. We got that. And then here we have the fraction. 3 times pi over 12 is 3 pi over 12. That is pi over 4, isn't it? So we are good here. That is correct. And so now we have our transformations very visible to us. No problem seeing what they are. So our amplitude in this case is the absolute value of 4, and that's 4. There's no reflection about the x-axis because that 4 is not negative. Remember, I put the 4 in the absolute value to remind you that the amplitude is the absolute value of the A value. And let's see, our frequency is 3, B is 3, and now we can see what the C value, the phase shift is. It's pi over 12, and because it says minus pi over 12, it's a phase shift to the right. So that's a phase shift to the right by pi over 12. And then we have a vertical shift down. So there's a shift down by 1. Those are our transformations. Now at this point you can see why graphing trig functions may be a bit daunting when you think about how you've graphed over the years, and you usually use nice numbers down your x-axis like 0 and 1 and 2 and 3. Maybe 0 to 1/2 to 1 to 1.5, something like that. And now we're working with trig functions, and look at these weird radian angles. Pi over 12, the frequency is 3. That means, let's see, 3 wavelengths fit from 0 to 2 pi, and then we have this phase shift to pi over 12. It sounds like a nightmare, right? Well, this method is really smooth, and it's really easy to use once you get it down, and it's all because we're going to be using the quadrantal angles, and we're going to change them so they're customized for this function, and our graphing grid will be totally custom, and it's going to be really easy to use once we have it set up. So what do we do next? Well, the key thing here again is to remember we've got these normal quadrantal angles from 0 to pi over 2 to pi to 3 pi over 2 to 2 pi. Well, we have to adjust for the new period. The new period, we found it, didn't we? Oh, and here it is. It's 2 pi over b. We've got to divide 2 pi by the frequency. So that's 2 pi. The frequency here is 3. The new period is 2 pi over 3. That means we're going to fit 3 periods of this cosine in an angle spread of 2 pi radians. And this, as I like to say in class, is if you were playing with a slinky and you held it in your hands and you were to push it, the ends closer together, push your hands closer together while you held it, the coils in the slinky would compress, wouldn't they? They'd come closer and closer together, and that's what's happening in this cosine wave, in this sinusoid. The wave is being squished, and so there will be 3 full wave patterns, 3 full wavelengths over a 0 to 2 pi range of angle values. It's also technically a horizontal compression, but for waves, for sinusoids, it's known as the frequency. So that was important, and now at this point we have to adjust our quadrantal angles, and we're going to use the period to do that. So we're going to adjust the QA, the standard QA. So the standard QA for the cosine, we go from 0 to 2 pi, right? Well, there's a middle angle. Midway between 0 and 2 pi is pi, and then midway between 0 and pi is pi over 2, and midway between pi and 2 pi is 3 pi over 2. Well, these angles are out. We've got a frequency that's going to fit 3 whole wavelengths in here. And so this is going to be different, and it's not going to be too hard to find. What we're going to do is this. We're going to adjust angles on the angle on the right end here first, because that angle is now not 2 pi, it's 2 pi over 3 if our first angle is 0. And then we're going to leave some blanks. And now this is the new period length that we see right here. Now what's the middle value between 0 and 2 pi over 3? Well, you need to be adept with your fractions, and 0 to 2 pi over 3, halfway is pi over 3, isn't it? Because 1 pi over 3 and another 1 pi over 3 gets us to 2 pi over 3. And now what about the midpoint between 0 and pi over 3? Well, here's where it helps to see pi over 3 as another fraction. It's 2 pi over 6. And halfway between 0 and 2 pi over 6 is pi over 6. And now if we look from the left, 0 to pi over 6 to 2 pi over 6, the next angle is 3 pi over 6. We just keep adding pi over 6. And then at the end, instead of having 4 pi over 3 here, excuse me, let's see if I can get my eraser working. Instead of having 2 pi over 3, we're going to use 4 pi over 6. It's easier to do these problems if you just use one denominator that works for all of your angles. We're not trying to show people that we know how to simplify what are already pretty simple fractions. That's not what we're after. We're after a good graph that's easy to put together. So we have the new quadrantal angles, but these are not the graphing quadrantal angles. And I forget if I called the graphing quadrantal angles up here. We're going to have to apply the phase shift. Now, where did I say that? Right here. And this is what gives us, I should change this to GQA. I've got a little typo here. So these give us the GQA, the graphing quadrantal angles. This is gold for us. Okay, so to get the GQA, we have to go look at what the phase shift is, because the phase shift is going to move every single one of these NQA, either right or left, by the amount of the phase shift. The phase shift is to the right by pi over 12. So the phase shift is right by pi over 12. Now look at our NQA. 0, pi over 6. Oh, these are all in terms of 6 on the denominator. So to make this a little easier, let's change the NQA so that these are all fractions of pi over 12. Well, we have to multiply by 2 over 2. So we're going to get 2 pi over 12. We're going to get 4 pi over 12. We're going to get 6 pi over 12. And we're going to get 8 pi over 12. Aren't fractions fun? Okay, now we can do the phase shift. Now, to get the graphing quadrantal angles, to go to the right, these angles have to get bigger by pi over 12. So 0 plus pi over 12 is pi over 12. 2 pi over 12 plus pi over 12 is 3 pi over 12. Do you see the pattern? We're adding 2 pi over 12 each time. So this is 5 pi over 12. This is 7 pi over 12. And this is 10 pi over 12. And those are graphing quadrantal angles for the first period we're going to graph. These will be the first 5 angles on our graphing grid, which is, again, it's a custom grid. Next thing we need to graph with is we need values. So the normal values, I'm just going to call this V, for our cosine function, they are 1, 0, -1, 0, 1. And I'm not sure why I use brackets up here. I usually just use parentheses, but I'm not going to make a big deal out of that. Well, we have to get to the graphing values because this is the parent function. So we need to apply the amplitude and we have to apply the vertical shift. So let's go get the amplitude. The amplitude is 4. Well, really, it's multiplying by the a value, to be quite accurate. It's multiplying by the a value, it's 4, and then we're shift down by 1. Okay, so to each of these values right here, we're going to multiply by 4 and subtract 1. So 4 times 1 is 4, and 4 minus 1 is 3. 4 times 0 is 0, and 0 minus 1 is minus 1. Now notice we've got a 1 here and a 1 here, so that means this 3 has to show up here again because it's the same calculation. And this 0 right here, well, the 0 led to a -1, so the 0 here leads to a -1. So we have one more calculation. A 4, which is the a value, times -1 is -4, minus 1 is -5. And now we have the graphing values. So I'm going to highlight the things we need to graph with and the things we need to customize our grid with, our graphing grid, before we can plot points and draw a nice curve. We're almost done. Okay, I've got a graphing grid in here now. And so our first GQA angle is pi/12. And this is just my preference, but I tend to pick this angle, this vertical right here, to anchor my first angle, my first quadrantal graphing angle. And that's pi/12. The next, I go over 4 to this other dark vertical, and that angle is 3 pi/12. And these are going by 2, so the next vertical is a 5 pi/12. So I'm keeping 4 verticals, or 3 verticals in between empty. I don't usually use those, but that's my preference. I find that this graph is easy to read and it's easy to sketch on. So we got 7 pi/12, and then we go to 10 pi/12. Wait a second, that's a mistake, isn't it? You guys see that mistake? 1 pi, 3, 5, 7. This is a 9 pi/12 right here. You can often pick up a silly mistake like that when you go to this phase of the graphing. So that's 9 pi/12. Now we're going to do 2 periods. So there's, let's see, 1, 2, 3, 4. So I'm going to 1, 2, 3, 4. And now I'm going to label this point right here with an angle, my very last angle. And so since they're going by 2 pi/12, this would be 11 pi/12, 13 pi/12, 15 pi/12, 17 pi/12. And again, you can see that this is an unusual set of angles. We're not even starting with 0 over here at all. We're not going to bother with that at all. This is a custom grid. Now the next thing we need to do is we need to accommodate our most negative function value, which are the graphing values here, and that is a -5 right here. And so again, this is my preference, but I like to put my lowest value down here. You'll notice there are only 3 values, 3, -1, and -5. And so right in the middle, I'm going to put the middle value, and the middle value is -1. I really don't care about the increments. I just care about these 3 values being properly spaced. And then the biggest value is a 3 right here. And you'll notice that the span between -1 and 3 is 4, and the span between -1 and -5 is also 4. So this is in proportion. We are ready to graph now. And without even looking at the angles up here, we have those angles on our graphing grid. We just need to work with the 3, the -1, the -5, the -1, the 3, and then we repeat the pattern, and we will have a nice graph. So at pi/12, we have the value 3. And this is customary for the cosine. The parent function, cosine of 0 is 1. It has its maximum value at its first angle in its quadrantals. And then we go to -1, and that's the midline value here. The midline is halfway between the highest point and the lowest point, the maximum value and the minimum value. And then the cosine goes down here to -5. And then it hops back up to the midpoint, the midline, -1. And it pops up to 3 again. We're into the second period. At the beginning of the second period, this is the end of the first and the beginning of the second. And we're back down to here. And you'll see the periodic function has a very easy pattern to replicate. And now, with a little bit of practice, over time you can learn to sketch sine and cosine pretty well. It's a little bit easier on regular paper than on this computer screen, but it's working pretty well. Try to make these graphs curve nicely. The sine and cosine functions are very smoothly changing functions without jagged or edges or corners or any sawtooth-like pattern. That's pretty good. I can do better on the smartboard, I think, but that's a decent cosine graph. And we are done with the graphing. The last thing I want to do here, because I will ask you guys about these questions when I quiz you, so I want you to think about these things. One, we're always thinking about analyzing functions also, and the domain of the cosine or the sine is all real numbers, so negative infinity to infinity. And the range here, it's going to go from -5 to 3, and that includes endpoints. There's our range. And just as a note, the midline is at y equals -1, and that's this line right here, y equals -1. Okay, what else could we ask? Where are the maxima? Can we give 2 maxima? Sure we can. We can grab one right here, and we can grab one right here. So here are the coordinates. We're going to give the coordinates, basically the locations of the maxima. One is at pi/12, and the value is 3. And another one, it's over here at 9 pi/12. Its value is also 3. These are local, and they're absolute maxima. And we can see that a cosine function or a sine function will have an infinite number of maxima. And then we can also give 2 minima. And they're found halfway between the maxima. 5 pi/12 is 1. So 5 pi/12 and -5. And let's see, we got to figure out the other angle because we didn't label them all in. But let's see, this is 9, 11, 13 pi/12 is our other angle. Not 13 over pi, 13 pi over 12. And the value again is -5, and these are local and absolute minima. And again, they're an infinite number of minima on a sine or cosine graph. We are done. I think that's usually written after a formal logic proof. Anyway, take care, everybody. I hope that helped. I'll see you soon. Bye.